in the last class we did about the number system and its conversion. So today we will start with Boolean algebra. Okay. So Boolean algebra is nothing but it is a mathematical system for the manipulation of the variables that can have one of two values. Now what one of two values means? Either true or false. That is in a formal logic. But in digital system, these values are on and off, and on is represented as 1 and 0. And sometimes it is represented as high and low. Okay, so there are some variables and their complements, and these are sometimes called as literals. And these Boolean expressions are created by performing operation on Boolean variables. The Boolean operator can be completely described using a truth table. The truth table may be if it is a 2-bit 0, 0, 0, 1, 1, 0, 1, 1 like that. And the Boolean algebra comprises three things. First, a set of elements, that means any variables, an operator, plus, dot or complement. And last one is the plus is for Boolean sum and the dot is for product. And this is a dash or a complement. We are taking. Then these are the axioms and the laws of Boolean algebra. What are the laws? If 0 dot 0, then it will be 0. 0 plus 0, then it is treated as 0. 0 dash, that means this is a complementary form. 1. A dot 0, something multiplied or product of thing 0, the result will be 0. And A plus 0, if something is added with 0, then the number will be that variable A. And this is a pattern. If anything multiplied with a 0, then the result will be 0. Else 1 dot 1, it is treated as 1. Similar 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1 and 1 plus 1, 1. And 0 dash, that means 0 complement 1, 1 complement 0. So these are the Boolean algebra and its law. After knowing the Boolean algebra, then comes a very important thing that we call it as logic gates. Now what are these logic gates? These are the fundamental building blocks of any digital system. For example, in analog system, the components we are using either the capacitor, inductor, resistance, diode, transistor, transformer, anything or a battery. But here we in digital system we will be using this logic gates. These are the building blocks of the digital system. Why it is called logic gates? It is called so because of its ability to make decision. What decision it is making? Okay. And normally these logic gates are of two types. One is your basic gates and the other one is called as a universal gates. And there are three types of basic gates. One is AND gate, OR gate, NOT gate. And the second one is the universal gate. They are of two types. They are represented as NAND and NOT. NAND and NOT. These are called universal gates. Whereas OR, AND and NOT, these are called as basic gates. Now we will be reading their logical symbol and their truth tables. Okay. Before going details with these gates, truth tables and logical symbols, let us clear some other things, that is input and output of the logic gates can occur in two levels. What are the two levels? Just now I said either high or low, true or false, on or off, 1 or 0. Anything you can represent. Okay. And these logic system is again classified into two. One is called positive logic system, the other one is called as a negative logic system. Now what does this positive logic system means? Higher of the two voltage levels treated as 1 and lower level is treated as 0. That means if I give for example 5 volt for a positive logic system, it will be treated as logic 1. and 0 volt will be treated as logic 0. This is for positive logic system. But for negative logic system, higher voltage level is treated as 0 and lower level is treated as 1. How? For example, 5 volt will be treated as a logic 0 and 0 volt will be treated as logic 1. Now comes to this AND, OR and NOT gate. Just now I said these are the basic gates. Now we will represent these basic gates in their truth table, then we will draw their symbol. So first one is OR gate. So OR gate is having 2 input with 1 output. So if it is 2 input, the possible states will be 4. That is 0, 0, 0, 1, 1, 0, 1, 1. And its expression is represented as A plus B. Okay, don't confuse with the sum and OR. Here this is a OR gate representation. It is not a sum. But here the logical operator is represented as plus. Now, the condition for a OR gate is if any of the input is 1, then it is 1. Otherwise it is 0. Now, if you check the decision, that means any of the input is 1. Here we are having 1, 1, 1. So no doubt the result will be 1. Otherwise it is 0. Similarly for an AND gate with the same variable 2 input, but the notation is represented as A dot B, or here I have taken the variable x and y. You can take any variable x, y, u, v, a, b, c, d, whatever. So here the AND gate is represented as either you can write A and B or A dot B. And the conditions for OR gate is when any of the input is 0, then it is 0. Otherwise it is 1. Simple. When both the inputs are 1, then only it will be 1. If any input has a 0, then it will be treated as 0. These two gates, OR gate and AND gate, they are having 2 input with 1 output. But another basic gate, that is a NOT gate, it is a logic gate which is having 1 input with the 1 output. Means it is having only 1 variable. Suppose A, then it is denoted as A bar, or you can write as A dash. Similarly, you can take X or X bar or X dash. That means A means here the input may be either 0 or 1, and accordingly its result will be 0 complement is treated as 1 complement is treated as 0. Okay. So these are the truth tables of OR gate, AND gate and NOT gate. Now we will see its symbol, because these symbols are used for our digital circuit system. Okay. First of all, OR gate is represented as like this: A, B, A plus B. This is my OR gate. And for AND gate, it is treated as this: A, B, A dot B. And for the NOT gate, it is treated as triangle with a bubble, and if it is A, it will be A dash. So these are the logical symbol of OR gate, AND gate and NOT gate. Now comes to the universal gates. Just now I said the universal gates are NAND and NOR. The question is, why they are called as universal gates? They are called as universal gates because the Boolean functions can be constructed using NAND gate and NOR gates. That means from these two gates we can also derive other basic gates, that is AND gate, OR gate and NOT gate. Then what do you mean by this NAND and NOR? This is nothing but, if you know about AND gate, just put AND plus NOT. Then this will become as NAND gate. That means if you know the truth table of AND gate, then just put the negation of AND gate. This becomes your NAND. 0, 0, 0, 1, 1, 0, 1, 1. For AND gate, if any of the input is 0, then it is 0. Otherwise, it is 1. Just vice versa for your NAND gate. A dot B, negation or complement. Similarly, OR plus NOT, it will become as NOR. And if you remember the OR gate truth table, you can write the truth table of NOT too. How? See, if this is having 0, 1, 1, 1, this is for OR gate. I will do the negation of OR, that becomes your NOT, because NOT plus OR. This will be 1, 0, 0, 0. Got it? Now how to do the symbol? Very easy. Just do the OR gate. Put a NOT gate. This becomes AB. Here it will coming as A plus B bar. And here it is coming as A plus B bar. And if I derive it with one logic symbol, it is denoted as just A, B and A plus B bar. Either you can represent in this way or in this way. But basically the logical symbol of OR gate is this. Similarly, the logical symbol of NAND gate is also same. A, B. If you put a bubble here, then this is treated as A dot B bar. So this is NOR gate and NAND gate. And let me tell you that from the NAND gate, we can derive NOT gate, we can derive AND gate, and we can derive OR gate. How? It is shown here. Normally, NAND gate is having two inputs, but NOT is having one input. So, how to derive from the NAND to a NOT? Just two input, you sort it and you will be getting the NOT one. Similarly, you know the NAND gate, just sort it, you will be getting NAND. Again, complement of NAND, you will be getting AND. And how to get using NAND gate, you have to implement OR. Just you put one NOT gate using NAND. Here it is coming as X bar, it is coming as Y bar. Now just put X bar dot Y bar, complement, you will be getting X plus Y. Why? Because X dot Y bar is treated as X bar plus Y bar, which is treated as X plus Y. Okay, that's why they are called as universal gates. Okay. There is another type of gate which is neither a basic gate nor a universal gate. But that gate is called as exclusive OR gate, or the other one is exclusive NOR gate. And for exclusive OR, the logical operator is, since it is a combination of OR, so A plus with the circle B. And exclusive NOR is represented as exclusive OR bar, or it is represented as this. Now what will be the truth table? Same principle. Just put AB. It is also having two inputs with one output, but here the condition is for exclusive OR, when both the inputs are same or when both the inputs are true, then it will differ. That means what? If it is 0, 0 and 1, 1 same, the result will be 0. Otherwise it is 1. Whereas for exclusive NOR, it is just opposite. That means the output of XNOR operation is true only when the values of the inputs are same. Okay. So this is exclusive OR and exclusive NOR. So these are all about Boolean algebra and its laws and logic gates. So if I recapitulate all these things, the logic gates are nothing but the building blocks of our digital systems, and they are of two types. One is your basic gates, other one is your universal gates. Basic gates are AND, OR and NOT, and universal gates are NAND and NOR. And other type of gates are XNOR and XOR. And this exclusive OR and exclusive NOT can also written as like this: exclusive OR or exclusive NOT. So this completes your logic, gates and Boolean algebra. In the next module, we will be reading about the classification of digital systems.